Hi everyone. I decided to make a video to kind of explain out some of the rest of our hypothesis testing big packet. As far as error goes, so this is pretty concise, but and don't worry too much about the power of a hypothesis test. We're not going to get into that. It's just nice to know that that's in there. This is from your reading. This is a nice, if you go down a little bit, right here, and I have one of these in your homework that you're going to have to fill out. Making a table really, I think, helps understand what we're talking about with type 1 and type 2 errors. So because what we're doing with hypotheses is we're splitting the world into two possibilities, either the possibility of the null hypothesis or the possibility of the alternative hypothesis, right? And we're saying only one can happen because they're paradigms of each other, right? They're not allowed to exist at the same time. So either your null hypothesis is true or your null hypothesis is false. Now, we can be certain to a degree that we're right, but we can never actually be certain which reality we live in, right? And so we have to then ask ourselves, well, what's the likelihood that we're getting this claim wrong? And that's really what errors are talking about. So if you live in the realm where your null hypothesis is true and you haven't rejected the null hypothesis, then you've done nothing wrong and you haven't made an error. The only error is if your data says reject the null hypothesis, right? And you have to go with what your data says. So it's not that you know that you're making the error, it's what is the likelihood that that error would be made. Same thing, if we live in the realm where the null hypothesis is false, right? And you reject the null hypothesis, awesome, your data went along with the reality of the world. But maybe you have bad data, maybe you did a bad job sampling, maybe it just was funny, maybe you didn't, maybe you did a perfectly fine job and it was just one of those moments in the world where data just is weird and funny looking, right? It happens. I mean, that's the problem with randomness, is that sometimes randomness is randomly, incorrectly observing what the rest of the data says. So it's weird. So these things can happen. And what we're looking at is what's the likelihood of these things happening. I really like this read for it, but I also have the read for it here. Okay, the next thing I wanted to talk to you about was actually calculating our test. So I have our standard errors for our single means here and here. Remember, you are very rarely going to be knowing the population standard deviation, which is when you would get to do a z-test. So oftentimes we are going to end up having to approximate that using the sample standard deviation. That's our little s here. And that means that our standard error is an approximation, right? So we're doing a lot of approximating, which means that we have to go for that single t-test. If you've forgotten about the difference between a student t and a normal distribution, you can go back to our previous weeks when we looked at that under the guise of confidence intervals. It's the same idea. Because it's, again, has to do with sampling distributions and how they're created. Remember, hypothesis testing and confidence intervals are really two sides of the same coin. We're looking at the sampling distribution and we're saying, how can we pick the sampling distribution apart to make it make sense for us? So we're essentially saying we know how the sampling distribution should be normal under certain conditions. And if we have those conditions, what can we say about our particular sample and where it should fall within the sampling distribution? That's really the crux of what we're doing with all of the stuff that we're doing. And again, here is our standard error for a proportion. Now, do be careful, because the way that we created the standard error when we had confidence intervals is we used p hat, because that was the only thing that we knew about with the proportions, right? We didn't know the actual parameter, that is the population's proportion. When we were doing a confidence interval, the only thing we knew was our sample, right? We just knew how many successes and failures we had. Here, what we have with hypothesis testing is we have our null value. So that assumption that we're making about the population, and there should be reasoning behind why we're making that assumption. So when we build the standard error, we're actually building it off of that assumption being true, because that's the whole point of hypothesis testing, is you are making an assumption about the population that you're holding to be true. And then you're taking your sample and you're saying, all right, how likely is it that this sample would exist if this assumption I made was actually true? And that is really what hypothesis testing is all about. So our standard error here is using the null value, i.e. P naught. So the value that you are using to make that assumption about the in your hypotheses. So the value that you use in your null and your alternative hypotheses. And in general, the way that we find our T or a Z is the exact same. So we do what's called standardizing. And the reason why you would have traditionally standardized is that you would be looking it up in a table of values to compare it. Nowadays, we don't really have to do this because we have all these calculators. But before, we would have wanted to do this because this is really basic math right here. So if I didn't have a calculator, I could do this very basic math. And then I would have a table of values to compare it to, which is what the critical value is all about. Whereas if I had wanted to do it by hand, if I didn't want to standardize it, I would have to be using advanced integral calculus to figure out the things that our calculators are calculating for us, because we're calculating area. And so since we don't have to do that, since our calculators are doing that, this is still just part of what we do. In case you're wondering, why are we doing this, as you're going to see down here. So I'm actually going to do the first practice problem with you so that you get an idea of really what we're looking for. So what we're trying to do is we're trying to see how the sample statistic, so your sample statistic, so remember your sample statistic is the X bar or the P hat, and then the test statistic is that Z score or T score. So test statistic Z and T, sample statistic X bar P hat. I know it's really hard because it's like so many of the same words. So part of why we're taking this slowly is to try and get us used to all that nomenclature and all that verbiage that is so similar sounding, right? It makes you want to pull your hair out almost. All right, so what we want to do is we want to calculate the Z statistic. So remember, our Z statistic in this case is our test statistic, because it's going to tell us about the test. We want to find the p-value. Now, I did not give us a level of significance to match our p-value up, so we're not going to make any end claims. We're just looking at how all these things look. And then I also want you to draw a diagram of the sample statistic. So in this case, our p hat in its sampling distribution, as well as what does the normalized statistic look on the standard normal curve. So we're going to compare the standardized test statistic to the sample statistic inside of the sampling distribution. Wow, isn't that a big mouthful? All right, so let's go ahead and do this. So let me close this out. So if we look at this, I have a sample of size n equals 500. Our sample proportion is 0.3. And then our null hypothesis was that P equaled 0.5. And our alternative was that P was greater than 0.5. So let's go ahead and remember, when I am calculating, the first thing we're going to do is calculate that Z statistic. So when I am calculating my Z statistic, the general, whoops, I'm so sorry. That was weird. The general idea why is it not copying and pasting? There we go. The general idea is that your test statistic, i.e. your Z statistic, in this case, now, if we were doing a studentized, it would be our T statistic. So our Z statistic, or test statistic is the sample stat, that's our p hat, minus the null value. The null value is the value that you're using to make assumptions about the population, divided by the null standard error. Now you can scroll back up and find the null standard error, but I actually have it already written out. Go ahead and paste that. And I think what I'm going to do is hit enter and make that on its own. And that one more down. So if you look, there's that 0.3, that's the sample statistic, minus the 0.25, that's the null value. And then down here, the null standard error for a proportion is the square root of the null value times 1 minus the null value divided by the sample size. And you want to remember that when you're working with proportions, you need to keep these. Our formulas are meant for when the numbers are in proportions. You don't want to turn them into percentages. That will mess you up and you will be sad. Okay, if we keep going, that's going to eventually pan out to be this. I can't believe there's not an equal sign there, so I will just throw a little equals in. It's going to look funny. That's okay. So it looks like our Z is 2.5819888897. Now, we might round this off to be about 2.58, depending on what calculator we're looking in. Notice that I did not, I tried to go out as far as I could with my null standard error. So when you are plugging this into your calculator, and let me just show you, I like to use Desmos. If you are calculating the Z by hand, I like to use Desmos. So the standard error is the square root, and then I will put in the null value and then do a divided by, because this turns out the nicest. Then I'll go back up to the top, put a parenthesis in, 1 minus my null value divided by my sample size. And there we, oop. It looks like I copied over my number. Oh, no, I didn't. Sorry, there's that. I was thinking about that 2.5. There we go. So that is how I would put this in. Now, if I wanted to calculate my Z value, what's cool is I can copy this in Desmos. So say you need to find your standard error, there it is. I can also, if it'll let me, hit copy. If I hit enter, there it goes. And then I can do that. Oops, there is my test, my sample statistic again, and there's my null value. My minus sign went away. There we go. And then because I copied this, I can hit paste, and you have to go do Control C, Control V. You can't right click on your mouse in Desmos, but this is a nice way to be able to easily calculate your Z statistic. And yes, you can calculate it in, there are calculators out there that will just let you plug in your numbers and calculate it, but it's nice to be, it's a fairly easy thing to calculate by hand. So it's nice to know, oh, I can just throw this into a calculator and calculate it by hand. And that's exactly what I've done right here, is I have calculated my Z by hand. And I'm going to go ahead and actually put that on the same line. I'll clean this up for us later. All right. So what we want to do, it says find the p-value. So let's go ahead to find the p-value. I actually need to stick that Z statistic in the standard normal curve. So I have, this is from your useful calculators. This is just the normal distribution. So it's centered at 0 and has a standard deviation of 1. Now, the reason why this number is normalized is, think about it. We are asking, what is the distance between the null value and the sample statistic? Now, the null value is where we are assuming, maybe actually, let's draw the diagram of the sample statistic and the sampling distribution. Let's actually do that one first. And then that'll make sense as to what we're doing with our Z statistics. So let's do that. So that is, let's put this number 0.3 inside of the sampling, the hypothesized sampling distribution that comes about from this. So here's our hypothesized sampling distribution. The hypothesis is 0.25. And then the standard deviation, well, that's our standard error. So I'm actually going to go borrow that from here. This number right here, that's our standard error. And one thing I do love about this is that you can copy and paste from Desmos into the normal calculator. Now, it did cut me off, but that's fine. I rounded out as much as I could. And when we look at this, we are doing a one-tailed test. And you can see we're pointing that way. I want to be greater than 0.25. So I am doing a right-tailed test. So I want to be above, I want to be above our number. And what number do I want to, what number am I curious about? I am curious about where my sample is laying. So 0.3, sorry, my calculators are all over. The number I'm curious about is 0.3, and we're gonna calculate it. And so you can see here is the sampling distribution where my mean is 0.25 and my standard deviation is this number down here. And where does a sample whose proportion is 0.3 fall into the sampling distribution? Well, it falls right about here. So it looks like it's about 1, 2, just under 3 deviations out in my sampling distribution. Now I could have looked at everything below 0.3. There's not really a way to do between or outside because I'm really only curious about this number. So I could have looked at it like this or like this. So let's go ahead and copy this image and we are going to paste it in. And I'm going to go ahead and make this a little bit smaller. And I think that there is a way to give it, maybe not. So instead, I'm going to say this is the sampling distribution. I'm going to say p hat. We'll need to insert equation. You can go \hat and then you go space p hat in the sampling in the specifically the null sampling distribution. Now we say null sampling distribution to identify that this is the sampling distribution that would exist if the hypothesized null value is true. That's what we mean when we say the null sampling distribution. All right, so here's where that sample that we got of 500 getting a proportion of 0.3, that's where it would fall in this hypothesized sampling distribution. So towards the upper end. All right, well, how does Z compare? And so let's take a look at what Z really means. So what we're saying here is we're saying, what is the distance between, let me actually do it in the normal distribution. What is the distance? The top part asks, what's the distance between the null value here and this sample here, right? That's really subtracting the two is finding what this full distance is. And then what are we doing? Well, look at what we're doing next. Then we're dividing by the null standard error. So I am dividing by the width of one of these standard errors. So I have a distance divided by these widths. So what this actually does is it tells me how many standard errors away those two numbers actually are, which is why when we're doing the test statistic, we go to the standard normal curve, which has a mean of 0 and a standard deviation of 1. And then I'm going to take my test statistic, my Z value, so 2.58. Let me go ahead and copy it from over here. And we'll just go as far as it will copy out. If you're having trouble with your homework and it not taking things, make sure that you don't round until the very end, that you try and round out as far as you can. And look at that. Is that not the exact same picture almost? And in fact, the only thing different between them is their labeling. There you go. And so then this one is the Z. I can't spell today. S-T-A-N-D-A-R-D, standard normal. So here's our Z-score, or our test statistic in the standard normal curve. And here's our p-hat, or our sample statistic in the null sampling distribution. So either way, this area here that's being created is the same. So in both cases, is what's our area? 0.0049. And that is your p-value. This is the p-value. And what that does, and I know that you've watched videos on it and you're watching more videos on it, and here's me saying it again. What this is this is the value, this is the probability that you would get a sample of this size with this, this is the likelihood that you would get a sample of this size with this sample proportion within this sampling distribution. So it's pretty unlikely, right? It's pretty unlikely that that would happen. That's not even a full percentage, right? That's even less than 0.5%. If you turn this into a percentage, that is less than 0.5%. So it's pretty unlikely. Okay, let's see. So that is, I think, everything I'm asking for. Let's see, calculate our Z statistic, draw our diagram of the sampling distribution and the Z statistic, and there is our p-value. All right, so that's what we're looking for. What we would have done from this point is we would have had we would have needed to have a level of significance to compare our p-value to. Because we don't have a level of significance, we cannot compare this p-value and make a claim as to whether or not we are going to reject or fail to reject our null hypothesis. It would be really unlikely that we would have a level of significance smaller than this, but anything is possible. So in this case, we probably would, but again, I'm not going to say that we do or we don't, because we don't have an actual level of significance to make that claim with. Okay, I hope that makes this make more sense. And that's all I got.